Hi there. Today I want to deal with topic 7, which is looking at the relationship between electricity and magnetism. And once we see that relationship, we can learn how generators, electromagnets, and then electric motors work. Let's talk about magnetism for a minute so that we can make this link between how magnetism and electricity are related. If we look at different types of magnets, what we'll notice about them is they give off an invisible force, which we call a magnetic field. And magnetic field lines exist even though we can't see them between the north and south of a permanent magnet. So in the case of a bar magnet, they go this way. And the Earth is like a bar magnet because it has an iron core. And so if we take the North Pole to the South Pole, we see these magnetic field lines, kind of like a bar magnet, which is why compasses work and they point north depending. Horseshoe magnet, very similar in that it has a magnetic field, which is an invisible force. So because of that, we can start to learn how to build important devices like electromagnets, which is a magnet made from a current-bearing coil of wire wrapped around a steel or iron core. So we're going to try this in class. If I take, for example, a battery with a wire, and I hook up a switch, and if I put the switch down, what I'm going to notice if I put the compass underneath the wire is the needle is going to deflect as soon as I turn on the electrical current. If I put the switch off, the needle points back to its normal direction. If I wrap the wire around the compass and then put the switch down again, I will notice an even bigger deflection in the needle. So here's what it would look like through animation. You notice a compass needle swings. It should be pointing north, but when we connect the wire to the battery, the compass needle swung because the compass needle detected a magnetic field nearby. Therefore, here's what we know. We know that electricity in a wire must create a magnetic field around that wire. So have a look at the animation again. This is what should have happened. So when current flows through a conductor, a magnetic field surrounding the conductor occurs. So if the flow of electrons from the cell, so this is the negative part of the battery, and electrons flow this way to the positive end of the battery, then the magnetic field would go around in this direction, which would be clockwise. And we have one way that we use in physics to understand which direction the magnetic force or the magnetic field goes. And so if you put your thumb, take your left hand, put your thumb towards the direction that the electrons are going, i.e. negative. They leave the negative pole of the battery to the positive. Your fingers represent the direction of flow of the invisible field that would be created. We call this the left-hand rule. So in this picture down below, if the electrons go this way, then the magnetic field this time around is counterclockwise because of that. It's clockwise in this picture. Now what happened when we coiled the wire? Why did the compass in our activity deflect even more? Well, you can amplify the magnetic field by making more coils on the wire, and that will make the magnetic field even stronger. So in general, when we take an electric current, the next thing I want to talk about is this phenomenon which was discovered, and that is if we take just a wire like this, and we move the wire back and forth over top of a permanent magnet, what we noticed was the light lit up, even though there was no battery attached. And so we call this magnetic induction. Somehow, because there are electrons in the wire, the permanent magnet can push the electrons along the wire, creating a weak electrical current. Now, based on magnetic induction and the fact that a battery can help push electrons, here's what we can do. We can magnetize this iron nail. We can magnetize it. So electrons go this way, they go through the wire, and they come back this way. But what that will do is that will create a magnet out of this iron core. So we call that an electromagnet. Let's look at this for a minute. Again, magnetic induction means that without a battery whatsoever, we should be able to take a magnet like this and move it inside a coil, and that will force the electrons to move. And so let's take a look at this, see if I can click on back to my normal thing. That won't let me click on that. So next, so here's our magnetic field, north to south. And now what do we have? We have a permanent magnet and we have a coiled wire. So what if we spun this coiled wire inside this magnetic field? What would that do if we use this crank? Well, what it would do is it would light up the light bulb. Okay, we call this a generator because we're generating electricity, because we know magnetic fields and coiled wire can make electricity by pushing the electrons. And this is an AC or alternating current generator, because what happens is current goes positive and then negative, positive and negative as we do this, because we're flipping this around. So here's another picture of what alternating current would look like. Well, what's about an electric motor? Electric motor is a device that changes electric energy to mechanical energy to do work. Here are two pictures. The first one shows you a complete metal ring and two magnets with a magnetic field and a coiled wire. We call this coiled wire an armature. And so if we spin this, we generate electricity, which makes alternate current. So this is what we call a generator. But watch in the second picture. What if we take the same situation, but now we create a gap between these two metal rings, so that when this spins this way, it reaches the gap. And we hook up a battery now instead of a handheld crank. A generator would have a handheld crank here. But what if we hook up a battery now through this, through the armature, and back to this end, the negative end? What we've just done now is this becomes an electromagnet. Okay? And it'll have a north and a south end. And when it spins, it's going to react with these two north and south ends of the magnet. So the bottom picture represents something different, not a generator anymore, but an electric motor. An electric motor has continuous motion, and it would create what we call direct current. And we don't need to do any work. We don't need to crank anything. So let's look at the parts to our electric motor. Let's put the battery here with the positive and negative and hook that up to the coiled wire. The first part to an electric motor I want you to be familiar with is the electromagnet. It actually has a special name. It's called the armature. and it spins in one continuous direction, and it'll change its polarity depending on what's happening here to this thing that now has a gap. Okay. Next, step 2 or part 2 to an electric motor is something called the commutator. And it is 2 split rings like this. These 2 split rings cause this to rotate in this direction, but what they do is they change the polarity of the armature. So as this is touching, it comes around, it hits the gap, and this one hits the gap here. What that'll do is, instead of this being north now, once it reaches the gap, it switches to south. Instead of this being south, once it hits the gap, it's north. Then it rotates again, and it'll switch polarities. A third part that you need to be familiar with for an electric motor is something called the permanent magnets, and that's these 2 things. Next, a source of electricity, which is a battery or plug-in. And third, brushes, which are the inside parts of the armature. So 4 parts to an electric motor. Let's see if we can see the 4 parts in this picture. Part A is here. What would that be? Well, that's the coiled wire that spins around. So that's the armature. The armature. Here's the armature in this electric motor. Part C are called the brushes. So part C, the brushes. Brushes. Part D, which is right here, those are the permanent magnets, the PMs, permanent magnets. And part B in the picture is the commutator, which is also located right there, the commutator. Okay. The only thing missing in this picture, we would have to hook up right here to these connectors a battery or power source, and then we'd have all the parts to an electric motor. So again, it's important to see the difference between an electric motor and a generator. This is a generator, and it's got a handheld crank, so we'd have to spin that. And when we did, there would be alternating current that would light up this bulb. Here's our armature. Generators have the armatures and they have the permanent magnets, but they don't have a split ring commutator. Okay, that's a big difference. Here's an electric motor. Here's our armature right there, very simplified one. Permanent magnet, power source. Just is missing a split ring commutator. Okay, let's go step by step on how this all works. Step A, electrons flow through here. They go through the armature, back through these, and to the positive end. So what that'll do is, that creates a north pole here and a south pole here. And when that happens, we know that north and south are attracted. So the armature starts to pull this way towards the north or the south end of this. Now this south end pulls towards the north part of the magnet, and that causes it to rotate slightly. As it rotates, the brushes start to reach these gaps. So let's go to the next picture. Once it's here in this position, the brushes are touching the electric gaps and the electricity is cut off thanks to the help of the commutator. Okay, there's no electricity. However, it still has momentum and it keeps spinning clockwise till it touches the other end of the brushes. Whoops. And once it's on the other side of the brushes, step C, what happens is this eventually here becomes north. So once it reaches this position, due to momentum, now that's north and this is south. Okay, this is south down here for the permanent and this is north. So what do we know about north and north? They repel or push away. Okay, so it pushes away and it's also now attracted here. And the cycle goes all over again. Once it reaches here,